In this demonstration, we will show you operation about the Granta interface provided by Multiscale.Sim. What you see now is a Workbench project window, which is a first view that appears when you start the application. The first step is to insert the analysis system. Here, select the appropriate analysis system according to the equivalent material constants we want to evaluate. To calculate the properties related to the structural analysis, insert the static structural analysis system. A drag and drop operation will insert the analysis system into the project schematic window. Within a single analysis, we will switch between the multiple applications as we perform operations. Basically, the applications are performed in order from the top of this list. First, starting engineering data. In this step, we define the material properties to be used in the analysis. This means the material properties of the materials that make up the microstructure of composite. We can also specify the value of the material property manually, but this time we will use the information registered in the engineering data beforehand. Lattice structures are created by 3D printing. There is a sample group of material property values for additive manufacturing, and we can select the titanium-based material from this group. The next step is to create the solid model in the geometry phase. This time, we will use the template for creating the lattice structure model, which is an add-on tool to Design Modeler. Here is a GUI menu for Design Modeler. First of all, set the unit cell to mm. There is a menu bar at the top of the screen labeled Multiscale.Sim. This is a template for creating the model for microstructure. We are providing many kinds of templates. Select the template for lattice structure from this list. Then, we specify the geometric information for each template from the detail view at the bottom left of the screen. Lattice shape name allows you to choose the topology of the lattice. We provide a total of 30 different templates for you. As an example, let's choose the regular cube lattice. The model is created automatically by just clicking the Generate button. This is the simplest topology for the lattice. We can really change all parameters even after the model creation. If you change to the different topology and click the Generate button, the changes will be reflected immediately. For the remaining parameters, length, width, and height represents the size of the unit cell. Each parameter refers to x, y, and z directions of the global coordinate system. Thus, setting the larger value for width will increase the unit cell that is longer than the y direction. One more important parameter is the volume content of the column, which is correlated with the thickness. So, reducing the volume content from 20 to 10% will create the model with thinner columns. In this demonstration, we will try to analyze one case using the cubic unit cell with a volume content of 20%. Then, launch the mechanical GUI. Almost all the work after this is done using the mechanical GUI. Here, the first step is to apply the material properties for each part that makes up the model. Since this is a single part model, we specify the titanium-based material for this. This material has been registered in the engineering data as I showed before. The next step is meshing. Ansys has a lot of options for meshing, but we will go with the default settings except for the slightly increasing the resolution. The mesh is a little coarse, but we will continue with it. For the analysis, where local stress concentration affects material behavior, such as a plasticity or fracture, a finer mesh should be recommended. The next step is to set the boundary conditions. The boundary conditions required for homogenization analysis are complex and very hard to define manually. Therefore, Multiscale.Sim automatically defines all of them. The homogenization settings object includes all of the boundary conditions definitions and post-processing for obtaining the equivalent material constants. In the detail view, enter the name of the material and any comments to supplement the description. These names will be registered in the engineering data and the Granta MI database. The test temperature is also specified. This is only necessary if the material applied to the part has a temperature dependency. In this case, we will set it to 30 degrees as a room temperature. Now we have completed the necessary preparations for the single condition. Press the solve button to start the analysis. In the analysis, a virtual material test is performed and equivalent material constants are evaluated using the results of this. After the analysis is complete, let's check the equivalent material constants. The results can be checked in the comment item. The equivalent elastic modulus as orthotropic anisotropy is displayed. In this case, the unit cell has a cubic shape, so the three components indicate the same value, but anisotropic behavior will be appeared according to the lattice shape. At the same time, the results of those analyses are output to an external file in the solver working directory. This file has compatible with Granta MI and contains not only information on equivalent material constants, but also input information such as lattice topology, unit cell size, and volume content. Unlike engineering data, the ability to register arbitrary information other than material properties is one of the Granta's good strengths. So far, we have shown the analysis procedure for the single condition. Next, we will demonstrate the operation of parametric simulation. In this analysis, the input and output information we want to change needs to be parameterized. Typically, this information is referred to as design variables. This time, we will set the lattice geometry parameters as design variables, specifically the lattice topology and height, and the volume content of the columns. The name of the lattice topology cannot be parameterized directly because design variables must be specified numerically. So we have prepared a separate ID number associated with the name of the topology. It is very easy to parameterize this. Just click on the square box to the left of the input field. Enter the parameter name and click the OK button to complete the parameterization process. The same procedure is used to parameterize the height and the volume content of the columns. The output parameters have to be parameterized. We also provide the object to check the equivalent material constants in the detail view. Using this object, parameterize all of the components of the elastic property. The procedure is the same as for the input information. Finally, we create a combination of the design variables based on the design of experiments. This task uses a feature in Design Explorer for creating the response surfaces. Insert the response surface system under the parameter set. When you open the Design of Experiments menu, you will see the list of input and output parameters that you make just set. What should be set here is the applicable range of the input parameters. In this case, we will use the value between 0.5 and 1.0 for the height. Following the same procedure, the volume content should be from 20 to 40%. Only the last lattice number is a little irregular. The ID number takes an integer value, in other words, a discrete value. For this reason, we will set the classification item to discrete and list the possible values during the analysis in the table. We will enter the total of 30 patterns of values from 0 to 12. The last step is to set up the design of experiments method. We will not go into the details here as they are not important for now. In the end, it automatically created 260 different combinations of the three design variables. When you click the Update button, the analysis for all combinations of design variables are performed one by one. When the analysis is completed, the information on the material constants will be output in the same table. In Design Explorer, this information can be visualized as a graph or response surface form. However, Since our goal is to export the data to Granta MI, so we will not show that. As in the case of single analysis, the analysis results are output to an external file in the format compatible with Granta MI. In this way, the results for each combination of individual design variables are output to the separate file. Let's actually open it up and take a look at the contents. You can see that the information is the same as in the single analysis I just showed you. Let's open the another file as well. Comparing the two files, you can see that the results for different design variables have been registered. So let's import this data into Granta MI server. Granta MI can be operated on the web browser. Now you can see the GUI for Granta Explorer, which is for referring to registered material database. We can customize the GUI flexibly. This time, we have added the menu dedicated to virtual material testing. When you actually open the menu, you can see the list of registered material data in the list format. As the already registered samples show, all the parameterized items in the Multiscale.Sim analysis can be registered. We can easily import the data. Just launch the menu for import and select all the external data obtained from the previous analysis by Multiscale.Sim and drop them into the Granta MI window. And then select the template provided by Multiscale.Sim. The data will be imported into the Grant server immediately. Here is our actually imported data. Among them, when you select one of the appropriate data, you can see the detailed information about its lattice structure. You can see that not only the material properties, which are the analysis results of the virtual material test, but also the input information are stored. In addition, if the materials for the columns that makes up the lattice structure are registered in the database beforehand, links to those materials will be automatically generated. In this way, by automatically correlating the relevant data, Granta MI is able to achieve excellent traceability in the material database. Let's try to draw the graph of the material properties using all the registered records. Here is the results. The vertical and horizontal axis can be set freely. Since the lattice structure is orthogonally anisotropic, simply changing the components used for the axis can result in dramatic changes in the shape of the graph. You can also add legends freely. In this case, we have added a legend for each of the lattice topology types. If there are too many plots to distinguish, select the topology you want to refer to from the list of the legends, and it will be highlighted. As the next, we will try to narrow down the data using material properties. You can use the slide on the left of the screen to narrow down the legends to be drawn. This time, we will search for materials with Poisson's ratio in the range of -0.5 to 0.5 and density less than 1000 kg per square meter. Any changes made on the slide will be immediately reflected in the graph drawing. In this search range, 3 lattice structures were left as candidate. If you want to check the specific value of each data, just return to the list drawing. Let's add these to your favorite list if you want to use them frequently in the future. In this demonstration, we have only introduced a very limited use of the solution. Nevertheless, you can see that there are many advantages in operating the Granta's material database compared to Workbench engineering data.